Alrighty. Can you hear me up the back? Okay, fantastic. My name's Tim. I'm currently working on a voxels-based stealth game with my brother back in Sydney, Australia. But until that hits the big time, my day job is as a developer on Bitbucket at Atlassian software. So today I'm going to be talking a little bit about my experience with using the Git version control system to version Unity games and give you some tips for collaborating on Unity projects using Git. Now, can I get a quick show of hands? How many people here are using some sort of version control for their projects already? Brilliant, almost everybody. How many people are using Git? Sorry, I already asked that question. I don't know actually how many people are using Git as opposed to just any version control system. Oh, brilliant, almost everybody as well. Cool. Well, we've got quite a lot of content to cover today. First, I'm going to give just a quick overview of why Git and version control are important for any software project, specifically games. Then I'm going to talk specifically about things you need to do to Unity to get it to work nicely with Git, and things you need to do to Git to make it play nicely with Unity. And then, since we're getting towards the end of the day, we're going to do a quick intermission that will involve a game with some prizes. Don't worry, it's not going to be one of those awkward introduce yourself to the person next to you games. It's going to be more fun than that. Then I'm going to talk about one of the biggest problems that you run into with using Git to version computer games, and that is handling large binary assets. Then we'll switch gears and talk about automating your builds. And then finally, I'll talk about tactics for branching and merging your code bases. So first, and it sounds like I'm among friends, so we probably don't need to spend too much time here, but why are we version controlling our projects in the first place? Version control is useful even if you're working by yourself as a solo developer on a title, because it gives you the important ability to go back in time when you screw something up. So version control is important for any project. But when you're working in a team, it's even more important, because version control gives you the ability to have multiple people modifying the same files concurrently, which you can't do without version control because you'd basically be stomping on each other's changes constantly. The other thing that version control is useful for is the ability to go back and see how your code has evolved over time. Because version controls don't just store revisions of your code, they also store some useful metadata, like the person who actually created the commit, when that commit was created, and usually a somewhat descriptive message of why they made the change. And this is especially useful when you're trying to trace bugs. If a user raises an issue with your product or your game, and you're trying to figure out what the problem is, you'll usually trace it down to a particular problematic piece of code. But then understanding why that code is there in the first place is something you need to turn to your version control system to inspect. So that's why version control is super useful. Git specifically is the best tool of choice for versioning games in 2017. The first reason for this is that Git is extremely quick. Using distributed version control systems like Git, after coming from a centralized version control system like Subversion or Perforce, is a completely different developer experience. When you type git commit or git log or git diff at the command line, the terminal responds almost instantly with your output and then the ability to run another command. Now, the reason for this is that Git is a distributed version control system. So all of the data that it needs to do to perform that command is already sitting on your local hard disk. It doesn't have to call out over the network to a centralized server. Now, the fact that Git is distributed and that you have a local copy of your repository, it has some other benefits as well. For example, you can work on things without a network connection. So this set of slides is actually versioned using Git, and I could tweak them on my flight from Sydney to San Francisco and create commits and evolve them without having to have a centralized network connection. And having a local copy of your repository is also handy for things like disaster recovery. Has anyone heard the story about how Pixar almost lost, or actually did lose, 90% of the assets used in Toy Story 2? So back in 1998, in a somewhat magical happenstance of timing, two senior editors were sitting there looking at some of the assets used for the Woody character, the cowboy in Toy Story 2. And as they were in this directory, looking at a network file share, suddenly the files started to disappear. And then all of a sudden they got a message from the OS saying that the directory that they're looking at is no longer valid. So they backed up a directory where they had the assets for Ham and Mr. Potato Head and Rex, and then they started disappearing as well. And then one of the senior editors tweaked and went, oh my God, ran into the server room, yanked out the power cable, because someone had accidentally run effectively a recursive delete of their file system. Now they did have backups, but as so often happens with backups, they weren't testing them properly. So they tried to do a restore and found that they were corrupt. Now fortunately, at this point, one of the senior editors stuck up her hand and said, well, I've actually got a copy of Toy Story 2 sitting at home. Because she'd been working from home after recovering from giving birth to her child, and had actually gotten a full dump of Toy Story 2 onto a Silicon Graphics machine that they had installed at her house. So they very carefully drove the SG machine over the Bay Bridge into the office. They called it like the $100 million Volkswagen in the story that I was reading about this. Gingerly plugged it in and managed to recover all of the assets. So using a distributed version control system like Git means that you are no longer dependent on a central server. Most people still use a central server. In fact, we're very glad that you do because we maintain Bitbucket, which is the central server. But even if that goes down, you're still able to work remotely. And if it goes permanently down, then you still have copies that you can use elsewhere. One of our competitors actually had a fairly serious data loss incident about a month ago, and that would potentially be terminal for other types of hosting companies. But for something like Git, even if they hadn't come back up, your source code is still secure because you have lots of redundant copies farmed out among your developers. Now, another really cool thing about Git is that it has awesome support for branching and merging workflows. How many people use branches as part of their dev workflow? Okay, cool. So maybe about half the room. So branches are really useful because they let you do parallelized feature work in isolated environments. So for example, in the game that I'm working on at the moment it's not the prettiest thing in the world. We've got sort of a working collection of shaders that work with most of the art in the game. But at some point, I'm going to have to go and rewrite those. And when I do that, I'm going to probably create a feature branch where I can work in isolation so that my brother can continue working on the game without my changes impacting his work. So we can still go design levels and work on other bits of isolated code. And then when I'm ready to merge those changes back into master, at that point, I can create a merge, and it will continue to work from then on in. So branches are a really useful way to have parallel streams of work without them intersecting with each other. And this idea of having isolated feature streams is really handy if you're in the post-release phase of the game when you're releasing patches, or if you're trying to release changes to a public beta, for example. You can have your master branch represent the working version, which is currently shipped out to your users. And then you can create individual feature branches and then merge them into master only when they're ready to ship. So this means the corollary of the isolated feature work is that you have a version of master that's always ready to ship. So these are all pretty good reasons to use Git, and I could talk for hours about the beauty of rebasing and interactive rebasing and the stash command and all the other cool stuff that Git gives you. But the simple best reason to use Git in 2017 for any software project is good old-fashioned peer pressure. Oops. There we go. So so Bitbucket actually came to Atlassian through an acquisition back in 2010. Back then, it only supported Mercurial. Are there any Mercurial users in the room? Hey, awesome, a few people, brilliant. It's like 5 or 6. Back then, it only supported Mercurial. We added Git support the same year we acquired it, and now Git is roughly 92% of Bitbucket. So it outnumbers Mercurial by about 11 to 1. Now, we still try and keep as much feature parity between the two version control systems as possible, with one notable exception that I'll be talking about later in this talk. But even outside of Bitbucket, various developer surveys from 2016 put Git at somewhere between 70% and 90% of the market. Now, this is slightly different in game dev, where there are a couple of incumbent centralized version control systems that are very popular, but the shift is definitely towards Git across all industries. Now, the reason peer pressure is important is because that means that all of the support and tooling and even the hiring pipeline gets easier if you adopt Git as your version control system. If you have a problem with Git, you can Google for it, and there'll be thousands of Stack Overflow articles and tutorials and things that you can use to resolve your problems. Also, in terms of tooling, most tool vendors will start implementing Git for their version control system support first, and then start looking at the other ones afterwards. You may not notice that with Unity specifically, which has built-in support for a couple of centralized version control systems, but certainly the code IDE that you're using alongside Unity probably has excellent support for Git. And in terms of hiring, Git is the #1 version control system taught at universities, and you're far more likely to hire a developer or an intern who has Git experience than any other version control system. So now I'm going to talk a little bit about what you need to do with Unity to make it play nicely with Git. Now, I suspect since most of you are already using Git and Unity, you probably have already set this. But the main thing you need to do is in your Unity editor settings, pop open your edit menu and jump to project settings and then editor settings. And then there's two very important things you need to set. The first is this thing called version control mode. You should set that to visible meta files. Now what this does is the metadata about Unity assets that's stored in these files with a .meta extension. Those files can sometimes be written to disk as hidden files, so this makes them visible instead. Git actually doesn't care whether they're hidden or not, but in terms of the output that you'll see from Git or tools like SourceTree or Bitbucket, it makes a lot more sense to have Git consistent with what you have when you browse around on your file system, so I just recommend setting that to visible. The other thing you'll need to set is the asset serialization mode, and this is super important. You have to set it to force text. So for the assets that Unity creates, so things like your scene files and materials, if it's set to force text, then it'll write it out in a YAML-based text format instead of a binary format. This is important for a couple of reasons. The first is so that you can actually read the format, again, in tools like SourceTree and Bitbucket. But the second is that if multiple people work on the same asset, then if you have it serialized as text, then Git has a chance of automatically resolving those two streams of work for you. Whereas with binary files, Git never attempts to try and resolve that, at least with its default configuration. So if two people change the same asset, it will always conflict if it's binary. So that's pretty much all you need to do for Unity. For Git, you need to craft a thing called a git ignore file. Basically, this is a file that tells Git types of files, or actually names of files in your repository that it shouldn't track. There's a few things you need to add to this. The first is Unity-generated files. So these are files that are derived from your source code, but the way that they're generated can differ slightly on platforms. So if you do put these in your Git repository, then they'll conflict horribly when multiple people have them regenerated and push them to the repo. Also, they can be kind of large, so they waste a lot of space and increase clone and pull and push times. The other thing you need to add is files generated from your coding IDE. So depending on what IDE you use, I'm quite partial to JetBrains' Rider, which is their new C# IDE, but you could be using Concealo or Xcode or MonoDevelop or whatever. Whatever you use, just make sure that you've got the files that are generated from that added to your git ignore file as well, so they don't have that same problem with conflicting. Another thing you want to ignore is build artifacts. So some people do push builds into their Git repositories, but typically there's better ways to do that. I'll be talking a little bit about build artifact storage later in the talk, but usually it's better to either use like a network file share or have like a dedicated tool for binary management. JFrog has a tool called Artifactory or Bintray, for example, and then you can use that to distribute builds as well a lot more easily than having them straight in your version control system. And finally, the last thing you should be ignoring is operating system special files. So these are files generated by your OS. Typically they're hidden, but because Git doesn't care about hidden status, it will pick them up anyway. And again, these are things that can conflict if you decide to push them into your Git repository, and they don't really serve any real purpose being there. So just keep them generated locally instead. So my git ignore file is up at bit.ly/unitygit if you want to reuse it. However, there's a really cool tool called gitignore.io where you can specify basically your game dev stack, like your platform, your engine, your IDE, and it'll generate a git ignore file for you from templates, and then you can just copy that and chuck in your Git repository and be done with it. So that's basically the bits and pieces you need to know about Git and Unity for smallish projects. So you can get away with these settings for a lot of 2D games, some mobile titles. But for larger games or games with a bunch of people, with a bunch of people developing on it rather, Git has a bit of a small problem. And there's a reason why not everyone in the world is using Git for game dev just yet. I could probably more correctly state this as Git had a very large problem with storing binary files, specifically large assets. Unfortunately, in game projects, unlike a lot of other software projects, there's a lot of large stuff going on. If you have high poly meshes, or large animations, or big scenes, or lots of scenes, textures, sprite sheets, audio, video, all of this stuff can get really, really big. And because Git is a distributed version control system, you can run into huge problems with this. Now, to understand why Git has such a problem with large binary files, you need to understand a little bit about how Git stores data under the covers. Now, since most of you are already using Git, you're probably familiar with this concept of a master branch, which is basically the default branch in your repository. And a branch in Git is a super lightweight construct. It's actually literally just a file that contains a SHA-1 hash, which is the commit of an ID. The ID of a commit. And the branch, so a branch is literally just a file sitting in a directory named after the name of the branch. And then each commit has a reference to other commits in the repository. And then you can trace back through the history of your version of your Git repository by basically following this relationship. This data structure is called a directed acyclic graph. It's directed because each relation has a start and an endpoint. And it's acyclic because when you create a commit, it can only point to commits that already exist inside your Git repository. So the reason why Git has trouble with large files is related to the way that the content is actually stored in this DAG. So DAG stands for directed acyclic graph. Git ships with a command called catfile that you can use to inspect objects inside your Git repository. And if you inspect a commit, you can see that it has a reference to its parent, a reference to a thing called a tree, which is another type of Git object, which basically represents the top-level directory of your project. And then you have some commit metadata, so who created the commit, when it was created, and hopefully a descriptive message. So we can keep using this catfile command to traverse into a particular commit, and you'll see that this tree object has a reference to other tree objects and other things called blobs, which actually represent your file contents. So this tree is basically the same as our top-level directory that contains our Unity project. Now as we traverse, and it looks a little bit like a file system, you have the mode of the file, the type, and the SHA-1 hash of the object's contents. So every object that Git stores has one of these SHA-1 hashes. Sometimes people refer to Git as a content addressable file system because the way that it does lookups is by taking these SHAs and then looking at the object that exists in that location. You might have heard about the shattered vulnerability that Google discovered last week, or rather figured out how to do, where they managed to have two different PDFs that generated the same SHA-1 hash when they were hashed. So that has serious ramifications for Git because the way that Git disambiguates between objects is by having different SHA-1 hashes. However, there's some patches in the works to fix this in Git, so it's not going to be a huge deal. So anyway, we can traverse down through our tree until we get something that looks a lot like our Unity project on our file system. Now, Git actually creates a new one of these trees every time we create a commit. It has to create a new blob and set of trees leading down to that blob every time you change a file or create a new file. Now, because Git is content addressable, it's very good at reusing these objects if they don't change. But every time you make a modification, it creates a new one of these blobs and puts it in your Git repository. Now, this is fine for text files, which is why Git works totally fine for things like the Linux kernel or, well, any other large project that doesn't have a lot of binary assets. Because it actually delta encodes these when you do a Git push and they get transferred over the wire. But with large binary assets, and let's say for the sake of this example that my stealth-based game has an elephant as a main character, if I push a 50 megabyte texture of an elephant into my Git repository, and then I decide that I don't want my elephant to be gray anymore, I'm going to change the hue of that texture to pink, then it's going to double the size of my repository and create a new 50 megabyte blob to represent that new version of the file. And this is going to happen every single time I make a tweak to this image. Now, depending on the file formats that you're using, sometimes the delta encoding that Git uses under the hood helps a little bit with this, but the reality is that most binary formats are already using some sort of compression, so they don't tend to delta encode very well. Now this isn't a problem that's unique to Git. Perforce and Subversion all end up bloating their repository sizes as you add more content to them. The difference with Subversion and Perforce is that all of that content is on the centralized server, and when you do an SVN checkout, you basically only have the latest snapshot of that code sitting on your local disk. But because Git is a distributed version control system, once I've created all of these assets, I have to push them all up to the server. And then anyone else on my team who does a pull or a clone has to pull down every single version of that file. So this causes slower fetches and pushes, and then makes the load on the server grow, and that makes everything else slow down as well. And this is traditionally why people haven't used Git for versioning games that contain large assets. Unfortunately, there is a very good solution to this that I'm going to talk about in just a couple of minutes. But first, we're going to have a little intermission/break. And this is awesome that most of you are already using Git because it's a round of Git trivia. All right, so let's get back to Git's little problem with big files. And the story behind how this problem got solved is actually super interesting. Like many great stories, it begins in Paris 2 years ago on the 8th of April 2015 at the Git Merge conference, which is a big conference put on annually by GitHub, one of our competitors, to talk about Git and all things Git. So they invited us to come and give a talk, and we put together a talk around some new technology that we were building. And the day before the Git Merge conference, there's this thing called the Git Contributors Summit, where most of the core Git engineers get together with some Git vendors like Atlassian and GitHub to talk about what we're going to do with Git over the next 12 months. Now here, there was an Atlassian engineer named Nicola Palucci talking to a GitHub engineer named Rick Olson. And the conversation went something like this. Nick said, hey, Rick, we've been working on this interesting bit of technology at Atlassian that solves the problem that Git has with storing large binary files. So we've built an extension to Git in Go, and we're planning on announcing it during our track session at Git Merge tomorrow. And Rick said, oh, it's kind of interesting you say that, because at GitHub, we've been working on this solution to the problem that Git has with storing large binary files. So we've built an extension to Git in Go, and we're planning on announcing it during our track session at Git Merge tomorrow, directly before your session. In fact, like literally concurrent, consecutively on the timetable. And Nick, understandably, was like, what? It's a picture of James Watt, by the way. And Rick said, totes, it sounds like we've kind of built the same thing. And then this is where it gets really weird. Rick said, so what do you call it? And we said, well, we call it Git lob, like long objects like you'd find in a database, because we're basically storing big bits of binary data. And Rick said, that's weird, because we also picked a 3-letter acronym. We call ours Git LFS for large file storage. Now, after a bit of back and forth between Atlassian and GitHub, we decided that their name was actually better than ours. And we actually mothballed the project. It's actually open source under the Atlassian account up on GitHub, if you want to go check it out. But we started migrating all of the stuff that we had built over into Git LFS instead. So things like the SSH transport layer and a couple of the hook refinement things originally came from the log project. So this is actually kind of fun because GitHub and Bitbucket have traditionally been fairly staunch competitors, and now we're working on a joint project to basically help people store large content. And it's especially good, I think, that this is a joint project because LFS is one of those things that could have potentially fragmented the Git community. Git is itself an inherently portable data format, very easy to move from one provider to another, or even to host your own Git server if you want to. So the fact that we have an open standard that multiple people can use is, I think, a really good thing for the community. Now, the way that Git LFS works is instead of storing your large elephant textures and other binary content directly in your DAG, instead, you move your large content into a separate file storage area, and you store these little pointer files which reference that content. Now, the beauty of Git LFS is that all of this stuff happens magically under the covers for you, and you don't have to really change your existing Git workflow. So when you run a Git push, these large objects get shunted into an LFS store, usually co-located with your Git provider. So Bitbucket has an LFS store attached to it. And then the rest of your content goes into your Git store as normal. Now, the savings come when you run git pull, because when you run a pull or a clone, your repository content gets served from your repository provider, and then Git LFS only downloads the large objects that are actually being checked out. So typically, this is the commit at the tip of the branch that you just updated. And then if you go back and, If you go back and check out an earlier commit, then it goes off and lazily downloads the content that's needed for that to actually fulfill that commit on disk. So it sort of breaks the distributed part of Git, but in a really good way. Because instead of getting the full history of all of these massive assets, which will slow down everything, you only pull down the versions of these large files that you actually need. And you still get a lot of the benefits of distributed version control because you can still create commits locally, you can still run all of your Git commands locally as well, as long as they don't actually touch versions of these files that need to be downloaded. You only actually need network when you need to lazily retrieve one of these things. So we can whip out our git cat file command again and look at the structure of one of these pointers, and you can see that they really are tiny. Instead of a 50 megabyte texture, we have a couple of 100 bytes with a version URI, which is basically a fancy way of doing version numbers, an object ID, which is a SHA-256 hash of the object's contents. So it's also content addressable, but it's using a slightly newer hashing version, so it will hopefully not have to change too much until someone breaks SHA-256 as well. And then we have the size of the object in bytes, which is used basically just not for verification, but for status progress output when you're pushing and pulling. Now, Git LFS is really easy to install. You just have to have the Git LFS binary on your path. So if you use a package manager, it's available for most package managers, at least on OS X and Linux. For Windows, I think you can just literally download it and put it on your path. And then you just need to run the git LFS install command once, and then that's it. It will start working. Now, the only thing that you need to do with Git LFS is tell it which patterns you want to start tracking using it. So, for example, for our elephant texture, we can say track all PNGs using LFS. Now, what this does under the hood is add an entry to a Git attributes file, which is a little bit like a Git ignore file, but rather than just saying ignore these, it means use these filters to process these files when changes are added or checked out. Now, are there any source tree users here? Source tree? A few people out of the room? Cool. So source tree, another fun bit of trivia, is actually written originally by a developer named Steve Struding, who happens to be one of the core contributors to the Git LFS project. So source tree actually has really, really good Git LFS support. If you install source tree, then it comes with its own version of Git and its own version of Git LFS. So if you're on Windows or Mac, an easy way to get started with these is just to install source tree instead. And it's also got a couple of cool little features, like you can right-click on a file and say track files of this type using LFS, and you don't have to worry about running that LFS track command yourself. Steve Struding's actually a super prolific guy. He also invented the Ogre 3D game engine. I'm not sure if anyone's used that. It's used on the Torchlight game series. But yes, he's done a really, really good job of getting this LFS support into source tree as well. So that's how LFS works in a nutshell. With Unity specifically, there are a couple of different file types that you definitely want to track with LFS, and then some stuff that you should probably just keep with standard Git. For LFS, you absolutely want to track things like sound effects and music, textures, sprite sheet, and full motion video if you're using those for cutscenes or something, because this stuff tends to be very, very big. For things like meshes and animations and scenes, if they're large, then you should absolutely track them with Git LFS. There isn't a lot of overhead for Git LFS, except for the fact that those files are no longer distributed with the core repository. So if you want to work offline, it can be convenient to have some of these things tracked in normal Git instead. The rule of thumb really is if it's a large file or a file that changes frequently, then you should use LFS. Small stuff, even if it changes frequently, is fine in normal Git, so things like text files. But if you have like a 500 kilobyte scene, if that scene changes 10 times a day, then that's going to be 5 megabytes per day that gets added to your repository. So you just have to sort of use, the two different heuristics of how often it changes in size as a bit of a gauge for whether you should track it using LFS or not. Things that you probably shouldn't are code, materials, because they're little, and fonts, not because they're necessarily little, but because they don't change very often. And potentially text as well, unless you're creating your own fonts, in which case, yes, you might want to track that with LFS as well. Now, the commands, which you're probably familiar with in Git, things like pulling and checking out and adding and committing, are exactly the same in Git LFS. So there have actually been attempts to solve the problem that Git has with large files before. There's a tool called Git Annex, another one called Big Files, Git Fat, Git Media, and all of these worked reasonably well. But they all put a bit of an unreasonable burden on the client to have to set up configuration with basically a file store or another content store. The nice thing about LFS is because there's a significant amount of the large file tracking logic is baked into the server. So when you do a push or a pull, Bitbucket actually sends down some storage URLs which can be used to store your content and download your content. And this is all handled by the Git LFS client for you. So you can literally use exactly the same workflow that you're using currently with LFS, and it should just work. The way that this works is that when you run a command like git add to add a file to your repository, instead of just taking that content and dumping it in your Git repo, it gets handed off to a special thing called a clean filter, which can be used to intercept staging calls to your Git repo. And then the actual content gets written into this like local Git LFS cache. It gets SHA-256'd. And then that SHA-256 hash is written out into one of those pointer files that we were looking at before. And so the only addition to your repository is a couple of 100 bytes instead of your 50 megabyte texture. And then the opposite happens when you do a checkout. So as we saw before, when you do a checkout, that content gets lazily downloaded. The way that works is Git reads that pointer file back out of your repository, hands it off to a thing called a smudge filter. So smudge is the opposite of clean. It's used to, dirty up your files before it gets written to disk. It looks in that local repository for the piece of content matching that SHA-256 hash. And if it can't find it, that's when it reads through to the backing LFS store over the network. And then the user is presented with the actual large file sitting in their directory. So this stuff is all super interesting, but you don't actually need to know about it. As a developer, you add your large binary file. This happens magically under the hood. And then when you check it out, that large binary file pops out of your repository again, or out of your LFS store, and it just magically works. Similarly, when you're transferring files to and from the server, the only difference you'll notice is that you'll see some output saying that new large content is being pushed if you've created some new versions of your files locally. And when you run a git pull, you'll see the resultant checkout that happens automatically after the pull might download some stuff if you don't already have those large files sitting locally. There is one tweak specifically for game dev to Git LFS that I recommend. And that is if you're working on a team with specialists, or if you have some unusual stuff in your repository that you may not necessarily need to clone everywhere, then you can actually constrain the types of files that Git LFS checks out by default using exclude flags. So if you run the Git LFS fetch command, it will download binaries for your tip commit, except for anything that you list in your exclude flag. And if you have a specialist engineer on your team, you can clone just those LFS files instead. So if you've got artists or audio engineers or anyone working with a specific file type, then they can include only that in their working copy, and their clone will happen much, much faster. And you can configure these permanently with the Git LFS config flags as well. And the glob matching, so the patterns which we're specifying here, is exactly the same as we use in git ignore files as well. Same goes for the Git LFS track command that we looked at before. Cool, okay. So that's all I really want to say about large file stuff. I can definitely talk at length about migration and stuff at the end if we have some more time, or feel free, we can chat about it in the hall afterwards, or swing by the Atlassian booth anytime tomorrow. Right, so now I'm going to talk about build automation. So build automation is basically the practice of having someone else, or actually an automated system, perform your game builds for you. So it's basically an alternative to clicking File and then Build in Unity. How many people here do have some sort of build automation? So another system that builds their games for them. Okay, cool, about maybe 30% of the room, excellent. And how many of you are using Unity Cloud Build? Anyone? Okay, cool, about 10 people. I'll go into more about what Unity Cloud Build is in a second. And for those of you who aren't using Unity Cloud Build, how many of you are basically running your own build infrastructure? So something like Bamboo or Jenkins or TeamCity. Okay, cool, about 25%. So there's a few different reasons why build automation is awesome. The first is that build automation means that you are not personally sacrificing your own CPU and resources to build the game. As your game grows in complexity and content, your build times can go bigger and bigger and bigger and bigger. And unfortunately, if you cut your builds locally, then because it's such a CPU-intensive operation, you can't really do much else. You might be able to go check your email or your Twitter, but you certainly can't edit your game because Unity spawns a little modal dialog to prevent you from using the editor while the build is in process. This problem compounds itself if you're working with multiple platforms. So a lot of people, in fact, one of the beauties of using Unity is that you can package the same game on different platforms really, really easily. But if you build for both Android and iOS, then your game build is going to take at least twice as long. If you package for Linux and macOS and Windows, then it's going to take 3 times as long, potentially. And you have to, if you're targeting anything to do with Apple, then you have to deal with horrific signing processes, and it's not a lot of fun. It's good to automate that stuff instead if you can. Another reason why automating builds is good is that not everybody on your team necessarily has the ability to create a build. If you have QA testers or artists or animators or external beta testers, they may not have access to your source, or they may not be using Unity, or they may not be a licensed user. So they will basically come to you and say, hey, can I get a build that I can play with? And that means that you've got to create the build and then upload it to Dropbox or Drive or whatever you're using to distribute your artifacts. And this is a bit of a time suck. And it sucks for you because you're being hassled all the time as a dev. And it sucks for the artist or the QA tester or the beta tester because they've got to wait until you do this, until they can play the latest and greatest version of your game. Another really good reason for automating your builds is that it's the gateway to continuous integration. Now, continuous integration is this idea of as soon as you write a piece of code, it should be integrated with the rest of your team's code as soon as possible. So if 2 people make changes to a scene or to a piece of source code or to a shader and they conflict, then you want to know that as soon as possible so you can fix that, so you don't write new things that assume that the code you just wrote will be okay with everybody else. This is even better if you're writing tests for your code as well, because you can actually test that logical bits of your code continue to work. Even if they're compiling, sometimes people can make logical conflicts that make your levels unsolvable or make your game unplayable for some other reason. And the fifth reason why continuous integration and automated builds are super cool, I'm going to keep a secret for now, but to do a little bit of foreshadowing, it has something to do with the bucket in the bottom right-hand corner. But before we talk about that, I want to talk a little bit about Unity Cloud Build. So it sounds like there's a few people who are using it. How many people have actually heard of Unity Cloud Build before? Okay, cool, most of the room. So for those who haven't experimented with it yet, I've been playing with it a lot recently for reasons that will soon become apparent. But basically the idea behind it is that you have a set of build targets, which are usually aligned with the platforms that you're building for. Basically, you define a target for OS X and Windows and Linux, and then it monitors your repository, which can be on GitHub or Bitbucket or whatever Git service you're using. And then once your repository changes, all of these build targets suck down a new copy of your code and build it. And then they build it, and they host the artifact that comes out. I think in the back end, they're using S3 for artifact storage. And they send you a link so you can download it or share that with someone else to actually go and play your game. So this is really handy, but I've been playing around with the config options quite a bit, and there's some pretty cool stuff hidden in there. Like the default experience is really easy to get up and running with. You just literally give them a URL, upload an SSH key to your Git hosting provider, and then it just works. So it takes your default configuration and builds. But you can tweak the settings quite a lot. So for example, you can choose different branches to build. By default, a lot of people just use master, which is important for continuous integration. But if you have multiple feature branches and some of them are long-lived, then you can actually define new build targets that build those feature branches for you as well. So that's cool if you're working in a team environment, because you can go and check out stuff that people have been working on their own branches without having to cut a build locally. Also, they are incredibly comprehensive in the number of Unity versions they support. So if you're a relatively small indie team, you might just be pegged on the latest version of Unity and happy to keep running with the latest version of 5x. But if you're a slightly bigger, more mature game studio, then you probably have very strict controls over which version of Unity your developers are running with. And Unity Cloud Build supports every version of Unity back until 4.3.1. So if you haven't upgraded to Cloud Build because you thought you had to use 5x, go check it out, and it will actually use the correct version of the Unity IDE to build for you. It also has some pretty cool advanced options, so you can enable whether it's a dev build or not. So depending on whether you're going to ship your build externally or you want the extra debug information, that can be really handy. You can also define pre-export and post-export methods. So if you have other tools in your Unity build chain, you can actually trigger those tools automatically in Cloud Build for you. So you could shell out to another tool, for example, from within your build. Or if you're doing things like code generation or obfuscation as like a final step to protect your code, then you can trigger that as well. Plus, you can define a custom scene list. So by default, it will use whatever scenes you have configured for your build. Configured in your editor. If you want though, so like you could have a demo plan or something like that that only exports scenes used in your demo, and then have that running alongside your main build and share that with your beta testers or external people, or automatically upload it to a website as a nightly build. And I'm not exactly sure when this appeared in Cloud Build, but it's super awesome that it did. They also have support for unit testing. So how many people write tests for their games, out of curiosity? Hey, fantastic. Okay, it's more than I expected. So that's maybe about 10% of the room. So Unity has pretty sophisticated support for unit tests these days. These are awesome because, as I mentioned before, it allows you to verify that the behavior of your game is consistent over time, not just that it compiles. And you can specify a test entry point, and then you can also configure whether Unity will consider it a failed build or not after it's completed based on those test results. So that's Unity Cloud Build in a nutshell. A lot of fun and very easy to get set up with. Oh, and it's also free. So if you have a free Unity account, you can still run Cloud Build, and you get all of the functionality. The only thing that you're limited on is the number of builds that can run concurrently. And you said there's sometimes, I think they've got separate test infrastructure for the entry-level tier, so there's sometimes a bit of a queue before your build happens, but otherwise it's fully featured. So I mentioned the little bucket down in the bottom right-hand corner. And the reason I've been playing around with Unity Cloud Build so much recently is that I've spent the last month or so integrating Unity Cloud Build with Bitbucket. So for those of you who aren't familiar with Bitbucket, this is Bitbucket. And up in the top right-hand corner, we've got this little integrations list, which now has Unity in it. For those of you not using Bitbucket, definitely feel free to check it out afterwards, but you could maybe approximate this with other build systems as well if you like. So what this does is you enter your Unity build API key, and it links your Unity organizations to your Bitbucket account. And what that linkage does is the next time one of your Unity Cloud builds completes, is it will actually post the build result to Bitbucket, and Bitbucket will bind it to the commit that was built. So you actually get a list of all of the completed builds over the history of your repository. So if we open this one, for example, I've got 2 build targets defined, one for Mac OS X and one for WebGL. And it gives me a link to the build results, so I can go and inspect the logs. But it also gives me a link to the binary. And under the covers, the Bitbucket integration creates a share link using the Unity API. So you can actually take this artifact link and send it to somebody, and they'll be able to download it even if they don't have a Unity account. So it's a great way to be able to share binaries with external people, or team members who don't use Unity. And one of the other really cool things about Unity Cloud Build is they have support for the web player, and also the WebGL build variants. And instead of just giving you a zip to download, they actually host your game as a static website using the WebGL build. So you can click straight through from Bitbucket and play the code on the static website without having to download it and set it up yourself. So I've just set one up with this is using Space Shooter, which is one of the Unity tutorial projects. But it's a nice experience because you can kind of click through straight away and start playing without necessarily having to go and set it up yourself. So this is clicking through to the build results instead of just the artifact. And you can see here all of your build output. This is usually not typically very interesting unless the build has actually failed or has taken a really long time. You can figure out how to optimize it. But linking these build results to Bitbucket commits unlocks a few kind of interesting workflows. If the build fails, you'll get there is no artifact that gets generated, but you get a link to the build log so you can debug it. But for example, we're looking at a branch in Bitbucket at the moment here. So this is the list of branches, so basically work that's happening in parallel to the work on the master branch. So if I was about to go to a weekly demo session and I want to show the rest of the team what I've been working on, and my latest build is failing, or for example, if you're coming to GDC and you want to show off your stuff in your game and your latest build is failing, then you can go back to your branch and see historical builds for each commit, and then just take the last one that passed. It may not have the latest features, but at least you have a working build. Now, the other cool thing about being linked in with branches is it also links to pull requests. Actually, quick poll, how many people use pull requests to develop their game? A few people, okay, cool. So pull requests, for those who aren't familiar with it, is basically just a really lightweight form of code review. So since it's bound to pull requests, the reason I like it with Unity Cloud Build is you can actually go and browse the changes that have been made to the code. For those up the back, basically there's a couple of added lines that are spawning new bullets whenever the player fires. And as a reviewer, you can kind of come and see this code change and be like, okay, the gun fires 3 bullets instead of 1 now, I get it. But as a reviewer, you're probably going to want to go and actually play those changes to see how it affects the game mechanics. So with the WebGL build, I can just click through, play the game, and then immediately go. Okay, eventually immediately go. Yeah, so you can see now the gun's firing 3 bullets, but it kind of sucks. Like, it makes the game way too easy now. Which, I mean, you have to play the game to realize that that's a problem. And before this, I'd have to clone the repository or fetch that branch and then build it locally. But now I can immediately go, nix this idea and go, look, that's terrible, and decline the pull request. And being integrated with Bitbucket's pull requests also means you can have access to some of our workflow features. So, for example, if you're doing continuous integration and you don't want failing code to make it onto your master branch, you can actually prevent pull requests from being merged until there's a successful build. So this means that rather than reacting to someone pushing crappy code to master, you can actually physically prevent it from being merged until you have a passing build. One final cool thing that this enables, and I'm sure there's other neat stuff that this integration will give us in the long run. Well, actually, well, it also encourages people to chime in and say why they think the build is failing, which I guess is maybe mixed positive and negative. But we also have the ability to browse different types of assets in Bitbucket. We don't have support for everything yet, but for example here, if I've got an STL file representing one of the meteors from the game, or asteroids rather, then I can, as an artist, or as any user, look at the history for this particular asset, and then grab a build that is using that version of the asset. So imagine if I'm an artist, and I make some changes to one of my assets, commit it and push it to the repository, maybe using something like SourceTree, then rather than having to nag someone to incorporate that into the game and give me a build, I can just go and download a build myself and see what it looks like in the game without having to hassle anybody else. So this integration is live. You can see it in the integrations list in Bitbucket, or you can just have written a little blog and post about some of the cool stuff you can do with it there. So we've got about 9 minutes left. So the last thing that I want to talk about is branching and branching's ugly twin, merging. Now, I mentioned before that branching is a really cool way to parallelize feature development or streams of work inside of Bitbucket. But the only problem with branching is that eventually you're going to have to merge those things back together. Oh, man. Cool. And nothing fills me more with dread when I run the merge command in Git than when I see this phrase, well, auto-merging. What auto-merging means is that someone else has made a change to some of the files that I've just modified, and that Git is trying to resolve those changes with the changes that I've made. Now, in the happy case, this will just be like, sweet, like I resolved that for you, and then you'll have a new commit which represents your merge. But a lot of the time, particularly with Unity it seems, especially with scenes, you'll run into conflicts. Now, merge conflicts don't just happen when you merge branches. Even if you're just following linear development on master, or even just working by yourself, sometimes if you rebase, or if you stash, or even if you pull changes from your master branch onto your local branch, if someone else has modified the same file as you, you are potentially going to run into a conflict. And I always have the same reaction, and that is the dread, because resolving merge conflicts is really tricky. You have to try and divine what this other person has done and make sure that that still works after you resolve it. Now, Unity actually ships with a built-in tool that makes this really, really, well, potentially much easier than what Git can do. So the way that Unity serializes stuff in YAML format is you end up with a whole bunch of these universally unique IDs serialized out to this format. And then this big list of objects in your scene graph could potentially change order almost at random, it seems. And so sometimes you can run into conflicts in your scene file, even when you've changed completely different game objects or completely different properties on the same object, which aren't really logical conflicts, but the way it's been serialized means that they do conflict. Now, is anyone using SmartMerge already? Hey, fantastic. I love telling people about this because they see it and they're like, what? I didn't know this existed. I've been manually resolving conflicts all these years. So I'll show you how it works, or what it does first, and then I'll show you how to set it up. But basically, Git has this thing called a merge tool, which is a command that you can use to apply a tool to try and automatically resolve conflicts. And Unity SmartMerge, which is like a little command line tool that Unity ships with, if you bind it to your merge tool, then if you have conflicts sitting in your scene files or other Unity-generated assets that use that YAML format, it'll go through and attempt to merge them. And as long as you haven't made changes to exactly the same game object, or if you have changed the same game object, have changed different properties on that object, then SmartMerge typically can resolve it for you. There is one weird kink to it though, where it comes out and says, the file that I merged seems unchanged. And I think this is actually a problem with Git, not SmartMerge itself, but just agree with that and move on. To test that it's actually worked, just open the file in Unity, and if the file opens, then that means that the merge has been resolved because the little conflict markers won't be there anymore. Now setting it up, you can take a shot of this if you like, but I've documented it at bit.ly/unity-git. Basically, you define a merge tool that shells out to the Unity YAML merge tool, which actually ships with the Unity editor in the tools directory. You pass it some Git magic, and it works. There's also some properties you should set, this trust exit code, keep temporaries, and keep backup. That's basically configuring which merge artifacts, so the before and after versions of your files, whether they should be kept around or not. This is what I recommend. You can tweak that if you like. And then once you've got the setup, you can literally run git merge tool when you have conflicts, and hopefully at the other side you will get a merged scene or merged material or whatever Unity asset you have. So I think I've got about 5 minutes left. I might see if there's any questions. So the links that I posted before, you can check them out. If you're not currently using Bitbucket or Unity Cloud Build, definitely check it out. We have free academic tiers and reasonable pricing. Actually, we're really good for, what do you call it? Well, actually, we're really good for any team smaller than 5 because it's completely free. Yeah, check it out and let me know what you think. And if you like, you can follow me on Twitter. I tweet a lot about Git and Bitbucket and random gaming stuff. So thank you very much for your time.